Let us now take a closer look at the theory of equations. First, recall that a polynomial of degree n is a function of the following type. So a function px that can be written as an x to the power n plus an minus 1 x to the power n minus 1 and so on up to a1x plus a0. So it is a function which is a linear combination of constants an up to a0 multiplied with x to a certain power, and then the highest power indicates the degree. So we have degree n because the highest power in my polynomial is x to the power n. And in this case, so we will take that the coefficients a0, a1 up to an can be complex numbers. So we have complex coefficients instead of real coefficients this time. Let's look at how to divide two polynomials. So look at the Euclidean division. Let p of x and d of x be two polynomials. Two polynomials with d of x not equal to 0 and the degree. So degree we will denote as deg of p. So the degree of p of x is larger or equal than the degree of the polynomial d. Then there exist two unique polynomials. So two unique polynomials r of x and q of x with the degree of r equal to 0, or at least the degree of r strictly smaller than the degree of q. For these two polynomials, it then holds that p of x is equal to d of x times q of x plus r of x. In this equation, d is called the divisor, so we divide by d. Q is the quotient, and r is the remainder after division. So r is the remainder after division by d. There are two ways to find r of x and q of x. So the first one is the Euclidean division. The second one will be the synthetic division. So the Euclidean division is the long version. The synthetic division is a shorter version of the same principle. We will explain these two principles, these two divisions, through an example. So we assume that we want to divide the polynomial 3x to the power of 4 minus x to the power of 3 plus 2x squared minus 2x minus 1 by another polynomial being x plus 2. So what we do is we write p of x, so the 3x to the power 4 and so on the left side. So 3x to the power 4 minus x to the power 3, 2x to the power 2 minus 2x minus 1. And then we want to divide it by x plus 2. So this one we write on the right side. And then we just work step by step. So we work from the left side to the right side. The first term in p of x is 3x to the power 4. And then we see how often can we fit x, so the highest order term in x plus 2 into this. So that will be 3 times x to the power 3. Why? Because that way we get here, this is 3x to the power 4 plus 6x to the power 3. So we multiply 3x to the power 3 with x plus 2. And then we write the result below p of x with the corresponding grades one below the other. In the next step, we then subtract this result from the original p of x. So we do the p of x minus the result that we get through the multiplication. So the first term becomes a 0, which is what we wanted to obtain by just fitting x into 3x to the power 4. And then we have minus x to the power 3 minus 6x to the power 3. So this is minus 7x to the power of 3. Next, we drop the following term. So this one goes down. So it's here plus 2x squared. Because this term hasn't changed yet, We haven't done anything with it. We then look again, how often can we fit x from x plus 2 in minus 7x to the power 3? This is minus 7x squared. We multiply again minus 7x squared with x plus 2 and write it below p of x. So minus 7x squared times x plus 2 is minus 7x to the power 3 minus 14x to the power 2. And then we subtract this from what remains of p of x. So again, the first term becomes a 0. And then we have 2x squared plus 14x squared, which gives me 16x squared. We drop the following term, so the minus 2x. X now goes 16x times in 16x squared, so this is plus 16x. We multiply again, gives me 16x squared plus 32x. We subtract minus 34x. We drop the final term, minus 1. And then we obtain here minus 34, because minus 34 times x plus 2 is minus 34x minus 68. We subtract again, and here we obtain 67. So what we did is we divided 3x to the power 4 minus x to the power 3 plus 2x squared minus 2x minus 1 by x plus 2. We obtained a quotient, so here q of x is this term, so it's the one that we obtained by dividing. This is 3x to the power 3 minus 7x to the power 2 plus 16x minus 34. And then the remainder, this is what remains after division, which is 67. So we found r of x, we found q of x. This here is my p of x. This was d of x. And with these numbers, with these polynomials, we can write that p of x is d of x times q of x plus the remainder r of x. The second option to do the division is through a synthetic division. We will introduce the synthetic division also through an example or through several examples and in different steps. So we start off with dividing by a monic linear denominator. So monic linear denominator. Or divisor. So here in this case my d of x is of the form x minus a. So this is linear because the degree of d is 1. So it's a first order polynomial, x to the power 1 minus a. It is monic because the leading term is 1. So here the coefficient with x is just 1. As an example, perform the following division. So x to the power 3 minus 12x squared minus 42. And we want to divide this by x minus 3. First, again, you write the p of x, but this time you only note down the coefficients. So you write only the coefficients on the top. So this gives me then the coefficient is 1 for x to the power 3, minus 12 for x to the power 2, 0 for x. So we have to write down every coefficient, even if it is 0, and then minus 42 for the constant term. So these are now the coefficients of p of x. In the second step, we negate the divisor. So we negate d of x. So this then becomes minus x plus 3. And then in the third step, you take this negated divisor, so the negated d of x, and you write every coefficient of this divisor to the left of your polynomial, except for the first one. So minus d of x was minus x. We drop the first coefficient, the minus 1, and then we have here a 3. We then drop the first coefficient. So this one goes down and we write it below the line. Then we make the multiplication. So we multiply 3 with 1 and we write it in the next column. So here 3 times 1 is 3. We write it below the minus 12, so in the next column. Then we perform an addition. So we add minus 12 and 3. So minus 12 plus 3 is minus 9. And then we repeat these things. So here 5 and 6, we repeat them until we reach the end. So minus 3 times minus 9 is minus 27. We add it to 0 is minus 27. We multiply this minus 27 with 3, which is minus 81. We write it in the last column. And then again we add those two terms. So this becomes minus 123. Then we have to determine which part of this is the quotient and which part is the remainder. So for the remainder, you count how many terms there are on the left side of the bar. So you count how many terms there are here. Here we have one term, because it was a linear case. So this also means that r of x has to be a constant. So the degree of r of x is 0. Because the degree of my remainder has to be lower than the degree of my divisor, which was a linear term x minus a, so in this case x minus 3. The degree of d is 1, so the degree of r is 0. We write here a line. We just count the number of terms from the right side which correspond to the degree of r. So the degree of r is 0. We only have a constant term. We have here only one term in the remainder. So my remainder will be this one. R of x is constantly equal to minus 123. And then my quotient will be everything else. My quotient is 1, minus 9, and minus 27. So it is 1 times x to the power 2, minus 9 times x, minus 27. And so in this case we have p of x. So this was p of x divided by d of x. We found the remainder r of x. We found the quotient q of x. So we now found those polynomials in such a way that p of x is d of x times q of x plus r of x. Let us now expand this synthetic division. So we will no longer have a monic linear denominator or a monic linear divisor, but we will just take any monic divisor. So we still have a divisor which has a leading term of 1, but it can be of any degree. So here monic again, the leading term is 1. But my divisor can be of any degree now, not just the linear ones. As an example, take p of x equal to x to the power 3 minus 12x squared minus 42, and take d of x equal to x squared plus x minus 3. So here the divisor is monic. Why? Because here this coefficient, the coefficient for the highest order term, is equal to 1. My leading term is 1. And then we apply the same steps. So in the first step we write down the coefficients. So the coefficients of p of x is 1, minus 12, 0 and minus 42. So this remains the same. In the second step we negate d of x, so minus d of x now is minus x squared minus x plus 3. And then in the next step we will add these again to our division. So we write down the coefficients. Except for the first one again. We write them on the left, but we now write them in an upward right diagonal. So if we drop the first one, the minus x squared, the coefficients are minus 1 and 3. In an upward right diagonal means we have minus 1 on the left side, 3 on the right side. We then again drop the first coefficient, so this one goes down. And in the next step, again, we perform a multiplication. So we multiply this one, so this dropped coefficients, with all the coefficients in the diagonal. And then next, what you do is, if you have this multiplication, you place those entries again in a right diagonal. So place the resulting entries in a diagonal, so diagonally to the right of the drop coefficient. So basically it means that we have two coefficients on the right. One of them has to be below -12. The other will become written down below the 0. So we write it on a diagonal going from 1 to -42. And then we write the lower one first. So we have -1 times 1. This is -1, will be below the -12. 1 times 3 is 3, will be written below the 0. And so we see it forms a diagonal going upwards to the right of the one we had. We had two coefficients on the left side of the division. So it also means we have, after the multiplication, two coefficients, and they will be written in the next two columns. And then step 6, you perform the addition, but only for the next column. So in this case, you only perform the addition for the second column. -12 plus -1 is -13. And then you repeat the multiplication and the addition. So you have now a -13 as a dropped coefficient. You multiply with -1 gives me a 13 in the following column. -13 times 3 gives me -39 in the column 2 columns after -13. So again, we make a right diagonal starting from -13. We then perform the addition in the next column, so in the third column. 3 plus 13 is 16. And then basically you repeat this process as long as you can write all of the terms below another term. So as long as you can do the multiplication with all the coefficients on the left side and still write them in a column on the right side. So now we would have 16 times -1, which becomes written in the fourth column below -42. But 16 times 3 cannot be written in this scheme. So 16 times 3, if we would do it, it would be written in this column. But this column does not exist, so we cannot do an additional multiplication. So it means we have to stop the multiplication, we have to stop the process. Once you have stopped this process of multiplying and adding up, then you make the addition in all the remaining columns. So here we have one column remaining, the last one. We make the addition also here. This is -81. We then first again determine the remainder, so r of x. We know that d of x, the degree of d, is 2. We see here we have two terms to the left of my division, which means that I have to count also two terms here in my result. So it has a first order degree. So here, this means that the degree of r will be 1. So degree of r of x is 1. It is two terms. We count them from the right. So it is 16x minus 81. And then the rest, this part, will be my quotient q of x. Q of x has also two terms, 1 and -13. -13 is a constant term and 1 is a linear term. So q of x is x minus 13. And then the third case. So the third case for a division is we have a non-monic divisor, so a non-monic d of x. So basically here d of x can be any polynomial of any degree and starting with any coefficient. What you then do is you make it monic. So you make it monic in the way that you divide by the leading term. So what you want to do is have p of x. You want to divide it by d of x, but in this case d of x is some a times x to the power k plus some other terms. What you do in the first step is you obtain a new polynomial d prime of x as d of x divided by a, and so this is x to the power k plus some other term. So d prime of x is monic. So here we can use the division for the second case, and now we have to modify the final result. So what we have, or what we obtain, is then we get p of x. We divide p of x with d prime of x using the second step. So using the monic nonlinear divisor, we get a q prime of x times d prime of x plus some remainder r of x. So this is the division by the monic d prime of x. We then know that d prime of x is d of x divided by a. And so to get p of x divided by d of x, we note that this is q prime of x divided by a times d of x plus r of x. And so q of x, the quotient by division through d of x, is just q prime of x. The quotient that we obtain when we divide by d prime divided by a. So we have to divide the quotient from the monic division by the leading coefficient a. So what we see is the remainder by division of d prime or d is the same. So r of x does not change if it is a non-monic divisor. What does change is the quotient. So the quotient of division by d of x is the quotient of division by d prime of x divided by the leading term a.